I got it.
You do? That's good. You're a champion. Anyway, anybody else think they got it? Yeah? Yeah? Okay. I got good news and bad news. Raise your hand if you had 1/4 x to the 4th plus x squared.
Yeah, he said it's wrong.
Okay, if you had that, you get what I'm trying to have you do. You're all wrong, but you're not wrong. You're all wrong, but you're not wrong. There is.
Thanks, Dad.
There is an infinite number of answers because if you think about it, yes, this will give me the first term. Oops, you guys can't see that. Yes, that will give me the first term. Why? Because 4 times the 4th is 1, reduce the power, and there's my third. Plus x squared gives me the what? The 2x. But what if there was a third term? What if the third term was that? We wouldn't know, would we? So if you think about the definition of today's lesson is called antiderivatives. I think that makes sense because we just did an antiderivative, didn't we? And we talked about an idea of something being indefinite because we don't know what the actual derivative is, do we? It could be an infinite number of possibilities. We'll talk about how we deal with that, like +5 thing that I put at the end of there. We'll talk more about that in a few minutes, right? So this number right here is arbitrary, right? It could be any constant, couldn't it? Any constant, okay? So the good news, guys, is that that's the entire lesson, right? The entire lesson is we're going to just practice working backwards, okay? In finding antiderivatives. We're going to look a little bit at notation, okay? We're going to talk about some specific antiderivatives that we can actually evaluate if I was to give you a little bit more information, okay? And that'll be that. So, first piece of information is if I gave you f of x and I said give me an antiderivative of f of x, your question would be, well, Picardo, I don't really know how to do that notationally, right? So I'm going to say it again. If I say f of x is the original function, give me the antiderivative of f of x, there's really no way to notate that, is there? So the way that we do it is with a capital F. Okay, so capital F would be the antiderivative of f of x. Now, if I give you this, then I've given you a derivative, which means the antiderivative would be the original function without the what? Without the little derivative sign, right? Make sense? Okay. So this outlines the concept of what I just talked about. If I asked you guys to give me the antiderivative of x squared, you would say 1/3 of x cubed, right? Based on what we did in the previous problem, 1/3 of x cubed. But the problem is it could be 1/3 of x cubed +3, +2, +1. It could have nothing there. It could be -1, -2, or adding or subtracting any value, and we're going to call it c. We're going to say c is a constant. And what is that constant used for? It's used for antiderivatives. Okay, it's that value that we think could be there. We don't know for sure. All right, so what I have here, guys, is 5 examples of some antiderivatives, really, really simple ones. Okay, I want the antiderivative of f of x equals 2x. Well, the first problem you have is that you can't write anything that goes before f of x, which means I have to use the capital in this case. And what function gives me a derivative of 2x? Well, we just did it. It was what? It was x squared. But remember, there are an infinite number of answers, so what am I always going to put at the end of an antiderivative? Plus c. All right. What do I give you here? Here I give you a derivative, right? So the antiderivative is the original function, and I can call it f of x now, can I? What's the power on this x? It's a 1, right? So the antiderivative had to be a power higher than that, right? So it had to be something squared. Now, if your mind works like my mind, you are now taking the derivative of this. So you're saying, okay, well, the derivative of this is 2x. But I didn't want 2x, I wanted 1x. So what do I have to do to 2x to make it 1x? Divide it by 2 or put a 1 half in front. What else do I have to do? Plus c. All right, and we get to f prime of x. Now it's a capital F, right? Well, the antiderivative of that would be getting rid of the prime symbol. All right, well, let's use things the way they're intended to be used. What do I do to the power to get an antiderivative? I have to add 1 to it, right? Because to get a derivative, I had to take away 1. So 4/7 plus 1 is 4/7 plus 7/7, which is 11/7. All right, well, here's the hard part. I know to take a derivative of this, I got to bring this in front, right? So I have to multiply 11/7 by something to get 2/3. Guys, you just created an algebraic problem there, right? I have to take 11/7. I have to multiply it by something to give me. Solving that for a, won't that tell me what should go in front? Yeah. How do I get rid of the 11/7? Reciprocal, yeah. So what did the a value have to be? It had to be 14/30. And if you need to do that, you can always do that, right? What else do I have to do? Now let's not forget about our bag of tricks, because in calculus, bag of tricks says if we can make something look easier, it usually works when we analyze things, right? So what am I going to do here for g prime of x? Write it as x. All right, so what is the antiderivative of that? Well, what do I do to the power? Add 1, so what does this become? -1. And if your mind works like mine does, you're taking this and you're bringing it out in front to check your answer, but I didn't want -1 in front, I wanted +1 in front. So what do I need to put in front of this? A negative sign. If I put a negative sign in front, now it's +1x, subtract 1 to the -2, it works. What am I going to do? Let's see. So I would probably write it like this. And notationally, I write this as dy dx, which means what? The derivative of y with respect to x, which means your original function must have been in the form y equals, right? So what trig function gives me a derivative of cosine? Sine plus c, right? So what I've done here, guys, is I've given you 5 very, very straightforward antiderivatives, right? Now, can they get more complicated? Of course they can, because this is APCalc, and they will. And we'll look at a number of different ways to make them easier. But first of all, what I have here is a list of antiderivative formulas. Now, quite frankly, you already know pretty much all of these. Guys, all this right here is what we just basically did, right? We looked at power functions, okay? This one right here, and what does that say? Well, guys, remember, what's the derivative of natural log? It's 1 over x, right? So what's the antiderivative of 1 over x? It's the natural log. Well, this one's pretty obvious, right? Guys, if you know your trig derivatives, then you know what the antiderivatives are, right? So like, do you really need to go back and memorize these? I mean, if you already have, then great. And then what are these? These are the trig inverse derivatives, right? And we talked about maybe having to memorize these or maybe trying to actually figure them out. These are a little bit tougher to do. All right, so I give you something that is ridiculous looking. And what is your immediate thought when you see this? Let's make it one fraction. Let's make it simpler. Let's make it easier. Let's see if we can make it look nicer. All right, so 4 sine of x. Am I going to do anything with that, or is that going to stay the way it is? It's got to stay, right? Can't do anything with it. All right, x divided by 2x to the fourth. Can x go into 2x to the fourth? What do I get? 2x to the third. Can x go into the radical x? Well, what's radical x the same as? X to the 1/2. And what do I do when I divide, subtract the exponents? So this is a half minus 1. So minus x to the negative 1/2. X divided by x. Careful with signs here. Minus x divided by this. And then just be careful, guys. This is a minus sign, so it gets distributed to this, right? So it's minus 1 over x. And what I've done is I've just created a function that's a little bit easier to maybe analyze now, right? All right, let's see if we can do it. Antiderivative is, so what do I have to take the derivative of to get a sign? A negative cosine. Now, why'd you say negative cosine? Because the derivative of cosine is negative sine, so the derivative of negative cosine is positive sine. So this is going to be negative 4 cosine of x. Plus 2x cubed. What am I going to do to that power? I'm going to raise it by 1. But when I take the derivative of this, I get a 4 in front. I don't want a 4, I want a 2. So what am I going to put in front of this? A half, good. All right, don't let this be difficult. Add 1 to this, what do you get? So it's x to the half. But what did I want in front when I took the derivative of this? I wanted a negative 1. When I bring this in front, it's going to be a half. Negative 2. Because half of negative 2 is negative 1. Reduce it, and I got it. What's the derivative of 1? Oh, I'm sorry. What's the antiderivative of 1? X. Guys, here's the thing. Remember we talked about those who get hundreds on math on AP exams are few and far between, right? For a couple of reasons. If you had to find this antiderivative, you pretty much need to know that what? The derivative, I'm sorry, the antiderivative of cosecant squared is negative cotangent, because the derivative of cotangent is negative cosecant squared. You got to just sort of know that chart, right? You got to know what the derivatives are, which in turn means you know the antiderivatives. So this is going to be plus 7 cotangent of x. Why plus, by the way? Because the derivative of cotangent's negative cosecant, which is going to make that the negative sign now, right? And then what did I say? I said this is one that you want to have memorized, right? I'm going to put a C in a minute. I'm not done. I'm not done, because what's the derivative of natural log? It's 1 over x. So what's the antiderivative of 1 over x? It's natural log of the absolute value of x. Why does it have to be an absolute value, by the way? Because x is a variable, and what can I not take the natural log of? A negative value, right? And Shimal said it. What has to go at the end of this? Plus c. There you have it. So that's just practicing a whole bunch of them in one problem. Christina, what do you got? Okay, so I could write plus c here. I could write plus c here. The whole idea being, if you only had to do one of these, just don't forget the c. But if you're taking an antiderivative of this whole thing, then one c at the end suffices. Think about it like this. If I had a plus c and a plus c, those are both constants. What could I have done with those? Put them together, right? That's why I only need one. Cool? All right, so here's what we're going to do in the second half of class today. We're going to look at what's called a differential equation. What does the word differential equation sound like? Differentiate. So in other words, I'm giving you an equation that's been differentiated. What I want to know is the solution to that differential. The solution to a differential is, what did we start with originally? Well, your answer to that is going to be, well, Picardo, you said there's an infinite number of what? Of solutions because of the plus c. So what am I doing here? I'm giving you additional piece of evidence. And with that additional piece of evidence, we can actually get the exact equation. Let me show what it looks like. Can you guys give me an antiderivative of this? All right, I'm hearing a lot of people mumbling. X cubed plus, hang on, what about the 1? Plus x, right? And then plus c. So we all agree that that is definitely the antiderivative, right? So what does this additional fact say? It says in the original function, when you plug in 2, you get a result of -3. Sweet. What does that mean? It means we can solve for c. Which means we know the exact equation that gave us those two facts. So the original function of 10, x cubed plus x minus 13. Now, of course, guys, if you don't have this piece of information, you have infinite number of solutions. I'm going to make this look a little prettier, okay? Find the particular solution to this differential. So here's the derivative that they gave us. You guys see what I did with this? Because there's a -1, I put it on the bottom of this fraction, right? So this is my original equation. Oh, no, it's not. This is my differential equation. It's in the form dy dx, right? So that means that the original must have been in the form y equals. So what is the antiderivative of e to the x? E to the x. You're going to be like, well, hang on a minute. Is this like a reverse chain rule? Is this, do I have to do something with the net? Well, guys, what am I trying to find the antiderivative of? 20 times 1 over 1 plus x squared, right? 1 over 1 plus x squared has an antiderivative of tan inverse. So it's plus 20 tan inverse of x plus c. So again, guys, this came from my chart. This came from my chart. And what does our fact say? Our fact says when you plug in 0, you get a result of -2. What's e to the 0? 1. Good. Okay, guys, I want you to visualize your tangent curve. Got it? Where does the tangent curve equal 0? Where does tangent cross the x-axis? At 0. At 0, right? So this is 20 times 0 plus c. So c equals -3, which means the solution to the differential is this. Oh no. Oh, I think it's okay. All right. Well, welcome back from lunch, everybody. And for those of you watching at home. Hello, YouTube. What up? Don't forget to hit the old like button, subscribe, put your notifications on. I don't want to be famous. And I'd have to do, yeah. Huh? That's where we're going. Oh, I'm serious. That's where we're going. There's nothing. I'm not. There's nothing I could say.
Do a tutorial on how you like make your project.
Nothing I could say would be interesting. Nothing I could say would be interesting. Yeah, I know. Exactly.
I would watch that.
You know. Well, I watch like some of the things that my kids like watch. I'm like, what are you watching? It's like some like moron on like a roof with like, I don't know, with like what are those little cars? The little RC Hot Wheels, not Hot Wheels, the ones that are on the track. What are those things called? No, the little tiny cars, and you play them with the joysticks, and they go little slot cars. You know what I mean? They go in the tracks, little figure eights. Anyways, they must have bought like 200 kits or whatever, and they're up on the roof, and they're like making like the slot cars go like jumps from one house to the next, and like every like 2 seconds, all I hear is whoa, whoa, bro. It's like what? What are you guys watching? But it's insane. You guys watch that stuff too? Oh, all right. You know what? The only stuff I ever watch on YouTube is like, just like when people go nuts in like a store or like, you know what I mean? Like somebody like when people freak out and like somebody records it. I don't know. Just dumb stuff. Yeah, I think those are funny. Or like the guys who go around and they tell the cops that they don't have the right to pull them over and stuff like that. Or I don't have to answer questions. I don't know, just they're funny, man. You just sit there and you're like, what the fuck's wrong with this guy? All right. Yeah, all that's I don't know.
Oh yeah, those are
He's like, yo, I watch your
It's
show.
like, what are you doing here today? And he's like, nothing. He's like, well, it says here you were gonna bring some toys. What did you mean? All right, here we go, guys. What I've given you here is I've given you the second derivative. So this is still going to be a differential, solving a differential, except it means we're going to be working with multiple antiderivatives, right? So if I can take two derivatives, then I can, what? Take two antiderivatives, right? Two steps forward, two steps back in a sense, right? So here I give you the second derivative. What I want to find is the first derivative, right? So derivative of 12x squared is 4x cubed. Bless you. Plus 3x squared minus 4x. Oops. And plus c, right? All right, so now we want our first derivative. Oh, sorry. That is our first derivative. So now we want our, nope, original function, right? Because we're working backwards. All right, so original function, x to the fourth, x cubed, negative 2x squared. Ready for this? What's the antiderivative of c? Sure it is. Plus cx, right? So there you go. So think about what we just did right there. We know that there was, okay, not that there was, but the potential exists that there was some constant here, right? Which means when I take an antiderivative, it means that that constant had the potential to be differentiable when we take the second antiderivative. And Wolf said it. Well, because I'm taking another antiderivative, I have to add the c at the end. Of course, because I've already used c, I'll call this something else. Okay. Okay, so if this were a 5, what would be the antiderivative of that? 5x, right? So it's some constant, which means that antiderivative is cx. Everybody good? Okay, so here's what we're going to do. This says that within the first derivative, when I plug in 1, I get 3. Well, here's my first derivative, right? So when I plug in 1, I should get 3. All right, so what do we got? 4 plus 3 minus 4. That gives me 0. I'm sorry, that gives me 3 plus c, which means c equals 0. Okay. That's pretty telling, isn't it? That means that there's no what? This x term right here doesn't exist, right? That's not going to be there. All right. So we'll see how this next fact plays into it, right? This is for part A, by the way, okay? For part B, it says y of 0. What does that mean? It means within the original function, when I plug in 0, I get negative 6. So within the original function, what's the original function? It's this one. So within the original function, when I plug in 0, I get negative 6. And I get that. When I plug in 0, I get negative 6, right? So plug in 0, plug in 0, plug in 0. We know that c equals 0, so this would be 0 anyways, plus k. So what's the value of k? K has to be negative 6. All right, so have I solved the differential? Well, not until I write the final equation, right? So I know what the value of c is, I know what the value of k is. So the solution to this differential is that. That cool? All right. Over here, right? I already got the tools that I need for the job because it's all referring to the same problem, right? So it's saying, okay, well, what if y of 0 equaled 4 and y of 1 equaled 1? Okay, well, let's do that. So within the original function, right? By the way, don't be confused, guys. This problem right here has nothing to do with this. Okay, they're two separate problems. All right, except we already know that these two things are what we're using for this piece as well. All right, so when I plug in 0, I get 4. So if that's the case, what's my value of k, right? And then I have another fact, right? And what's the other fact? If I plug in 1, I should get 1. All right, well, let's see what happens. And so what did I do, guys? I used what? The answer from this to plug into this, right? And what do we get here? Well, we get that's 2 minus 2, so that's 0. So 1 equals c plus 4. So if I have those values, then using this problem, the solution would be that. Guys, I keep saying the same things over and over again, and I hope you're getting sick and tired of hearing it. But again, doing this process right here, would you not agree that taking antiderivatives can only be done if you really understand how to take a regular derivative, right? So we're still practicing derivatives, right? And then there's a little bit extra algebra that go along with it, right? But ultimately, same skill. This is where we're going to go next class. Okay, we're not going to actually even do this today. I'm going to give you some time to start some work. Okay, but what we're going to do is we're going to look at some higher level integrate. Okay, so new word, integration problems. Okay, the word integrate means to take a antiderivative. They are synonyms. Okay, so we're going to be learning how to integrate, right? Well, we already know how to integrate. These are just going to be a little bit more complex. And so what are the techniques going to be used to find antiderivatives of these, okay? So we're going to look at a little bit notation and then some higher level problems. Cedric, what do you think? Good?